Hello, Biol-50. Here we are again in Chapter 2. We're going to start Chemistry of Life, and we're going to be talking today about biological molecules. One of the things I like about this picture that I put up here is it highlights what the four main biological molecules are that build every biological organism, including humans. So there are, I'm trying to get my pen to work here. There's my pen. I think I'm going to use, let's use red today. Carbohydrates, which are sugars, lipids, which are fats and steroids, proteins, which are proteins. It's not, think of it more as than just chicken or beef or soy. Protein is a long chain of amino acids, which we'll talk about. And then you have nucleic acids. Nucleic acids are your DNA and RNA. Only these three, carbohydrate, lipid, and protein, can make energy, okay? And they come from things you eat, okay? So you have to consume carbohydrate, lipid, or protein to make ATP energy. And we'll get to that in another chapter, all right? Nucleic acids basically are DNA and RNA are no-cal, yay! No calories, right? That's okay though, because they also aren't used to make energy. So one of the things to think about is if it has calories, I mean, if we express calories as a part of the nutritional components of this molecule, then it's going to be converted to ATP energy. All right, so we're going to start with the basics of chemistry real quick. Chemistry and biology, one of the big jokes that we have in biology is you can't have biology without chemistry. However, having said that, no one can observe chemistry without biology working, right? So chemistry and biology are linked to one another. When we look at chemistry in biological organisms, about 65% of our body weight is made up of entirely oxygen atoms. Now, don't worry about what the oxygen is incorporated into, like muscle or fat or skin. We'll talk about that later. Chemistry is important for water to be able to do some of its special properties. So water itself has a lot of unique properties, which we'll review somewhat. Here you see this little water walker here balancing on the surface of just a body of water. And this is called surface tension. We're not going to talk about this a whole lot. I just kind of like the picture. Over here, we're looking at something called acid rain. And acid rain is when rainwater, becomes acidic, more like vinegar than regular water. All right. And what that does is it impacts organisms when you change the pH of liquid, especially water. So we're going to talk about pH and what does pH mean. And then one of the things to bear in mind is that there are a lot of different minerals out in the environment that are necessary for the functioning of life. Okay, so for example, iron. Iron is essential in mammals and some other organisms, but mostly in mammals. We'll focus on mammals because we're humans, right? We're mammals. Iron can be converted to hemoglobin, which carries oxygen in our system. Iron in the nail is in like a nail that you use to build something, is the same iron as what our bodies use to carry oxygen. So let's go through some basics of chemistry. Hopefully you'll remember this from your second year of high school. When you take a biological system apart, what you end up with are smaller units. And if you go smaller, smaller, and smaller, you'll end up at the chemical level, okay, where you're looking at things like atoms. So basically, at the chemical level, you're going to look at individual atoms or compounds where you put two atoms together to make something, all right? So elements are collections of all the same atom, okay? So collections, here comes my really swell handwriting, right? Let me see if I'm going to try doing something different here. I'm going to kind of you can't see it, but collections, I'd say pure collections of atoms. So like hydrogen would be elemental hydrogen, just H, right? Compounds are where you put two atoms together, two types of atoms. One atomic type plus 1. Let's make that look like the number 1 somewhat. Atomic type. Not much better, but a little bit better, okay? That's what a compound is, right there. So elements and compounds, by their virtue of being made up of atoms, are made up of matter. So matter is anything that occupies space, okay? And it has mass. I'd like to think about mass as weight minus the effect of gravity. So matter on Earth is found in 3 states: solid, liquid, and gas. So matter, for the most part, is made up of chemical elements, all right? And that would be this thing right here, the collection of atoms. So elements can be organized in such a way that we can look at them on the periodic table, and we'll look at that in a minute. But elements themselves cannot be broken down into smaller substances, okay? They can be broken down into subatomic particles, but you can't take hydrogen and break it down into something different. You can take a hydroxide or a hydroxyl and break it into an oxygen and a hydrogen specifically, right? Each one of these is an element. This is the compound. All right. So all the elements, all 92 of them, are listed on the periodic table. Now, some of these empty spaces here, we know something exists there. We just haven't found it yet. Don't worry about that. That's for upper division chemistry, you guys. 25 elements, however, are essential to life. And one of the biggest one is carbon here. Okay. Carbon you're going to find in what we call organic molecules. So 4 of all of the elements make up 96% of the human body, okay, the weight of the human body. Other trace elements, things like iron, occur in much smaller amounts. So oxygen, our body is mostly made of oxygen. Lots of carbon though, okay? So what I would say is oxygen is like the main scaffolding of the body. Carbon, however, is where you're going to see functional molecules being built. Hydrogen, nitrogen, trace elements, things again like iron. And then you have other trace elements like calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. Like remember sodium chloride? We'll get to that later. So why are these trace elements so essential? Turns out that trace elements help cells in the body do jobs. They actually act as what we call a cofactor, an enzymatic cofactor. Don't worry about what that means right now. It allows enzymes to convert one molecule to another. So let's say you have X, then you add an enzyme plus, here, I want to get rid of that plus. I don't like that plus. You have an enzyme with a magnesium, let's say, and then you'll get your reaction, and then you'll get your product. So one example of this is iodine deficiency in goiter. When people don't get enough iodine in their diet, their thymus is unable, their thyroid is unable to make T3 active components of T3, T4, okay? T3 and T4 are molecules that help set our metabolic rate. So it's essential for our body being able to do the job that it needs to do. Well, if you don't have enough iron, what happens is the body will grow what's called a goiter, which is an enlargement of the thyroid. And the thyroid will just keep trying and trying and trying to make T3 and T4, so it makes more cells to make T3 and T4, but that's all because it doesn't have the iodine, okay? If you give somebody iodine, let's say like in table salt, you'll never develop a goiter. So oftentimes you'll see things like a goiter in a third world country where iodinized products are not used or iodine is not present in their diet. Okay, so that's basic elements, the basic elements that make up the body. At this point in time, you don't need to worry about what a goiter is. We'll come back to that in another chapter. What I do want to talk about now is how elements come together to make a compound. Remember, we saw sodium and chlorine. You put sodium and chlorine together and they form salt. And it turns out that sodium and chlorine hang around together because chlorine actually steals an electron from sodium. Chlorine's a thief, okay? It tends to do that a lot. When that happens, it becomes sodium chloride, okay? The chlorine becomes chloride when it steals that negative electron, negatively charged electron, which means we have to talk about what atoms are made of. I'm sure you remember this. Atoms consist of 3 subatomic particles. And the nucleus is not nucleus, okay, guys? It's nucleus, nucleus. Nucleus just means center, center of an atom or center of a cell. Nucleus means center, okay, central region. The nucleus is made up, and I'm just circling it, of protons, positively charged particles, and neutrons. These guys have no charge, okay? Outside of the nucleus, you have what are called orbitals. These orbitals contain electrons. And in this orbital number 1, you have 2 electrons. There are more than one orbital, depending on how big the atom is, and we'll get to that in a few minutes, okay? This is orbital number 1. And so what's happening is you have basically a separation of the positive and negative charge, okay? And the neutral charge is just kind of mixed in with the positive. The electrons have basically no mass. Or another way of putting it is negligible. I don't have enough space. Negligible means virtually none, N-E-G-L, negligible mass. Protons and neutrons, they have mass. And remember, mass is like weight minus the effect of gravity. Why do I keep talking about gravity? Why does she keep talking about gravity? Well, gravity is different on, let's say, Earth and the moon. So the weight of a proton will be different on Earth and the moon because we have different levels of gravity. A proton will weigh more on Earth than on the moon. So instead of having that effect of gravity, we just say it has mass. All right, so the subatomic particles, proton, neutron in the center, nucleus, electrons orbiting around the outside. Most atoms have protons and neutrons that really are stuck in the nucleus. Sometimes you'll end up with an extra proton or neutron. Don't worry about that. But electrons always live outside in the orbitals. Now, one of the things that we look for in atoms is how many subatomic particles are in each atom. So the elements actually differ from one another based on the number of protons, neutrons, and electrons. So when you have something called the atomic number equals just the number of protons, okay? Atomic number of protons. The atomic mass is the number of protons plus the number of, what do you think? Neutrons. And the reason why we say that the atomic mass is the number of protons plus the number of neutrons is because when we come back here, electrons have negligible mass, virtually no mass. So even if you were measuring the weight of an atom, the electrons might not even make a difference, but the protons and neutrons would. So think about it like in terms of weighing yourself. If you're going to weigh yourself, let's say when you get up in the morning and you just have your pajamas on, you basically have a bunch of electrons, right, just around you, which would be your pajamas. Now, if you put a whole bunch of other clothes on, or let's say, for example, even more appropriately, you eat a huge breakfast, a bunch of eggs, toast, sausage, bacon, 2 big glasses of orange juice, a cinnamon roll, my favorite part, okay? You do all of that, you're going to be sticking things that have mass into your center, right? You're going to be increasing your nuclear size there with all that food, and your atomic mass or atomic number will go up. The atomic number, not so much, sorry, the mass will go up because you've increased the number of protons and neutrons or food in your stomach. I hope that helps. Again, I use food for a lot of examples. If it doesn't make sense, I'll try another one. Send me an email. I try, okay? Mass, again, is the measure of the amount of matter in an object, how much of it is there. Okay, so carbon 12 is neutral carbon, has 6 protons, 6 neutrons. So the atomic mass is 12 because it's 6 plus 6. What's the atomic number? The atomic number, remember, is just the number of protons. The electrons aren't going to make a difference. Now, one of the things that can happen in an atom is that an atom can get most easily extra neutrons. Don't worry about why, okay? That's for the physicists, all right? Don't worry about why. But let's say carbon gets an extra 1 or 2 neutrons. Then you'll have carbon 13 because now you have 7 neutrons, or carbon 14 because there are 8 neutrons. Carbon 14 is a byproduct of an atomic reaction where hydrogen breaks apart and things happen in the environment forcing extra neutrons into carbon, okay? You don't need to worry about all that again, but the idea is that now you have an atom that has extra neutrons, so it has a higher mass, right? It's 14. But another side effect of this, having those extra neutrons, that makes the carbon excited. We say it's excited. It's full, it's extra full. So what the carbon's going to do is eject one of the neutrons out, okay? And after a period of time, it'll come down to carbon 13. At some point in time, it'll eject out the other neutron, and it'll decay back down to carbon 12, all right? So that's called radioactive decay. So carbon 13 and 14 are considered what we call isotopes. They're alternate forms of an element, okay? They have the same number of protons and electrons, but they have a different number of neutrons, and it can eject out those extra neutrons, by which you'll have radioactive decay. And the thing is, when you have radioactive decay, especially these neutrons jumping out, that's a very high energy process, and those neutrons can actually penetrate human skin, interact with DNA and damage DNA, cause mutation. Okay, so that was isotopes, all right? Isotopes can be used in medical imaging. There are some isotopes that aren't dangerous, some that are, but you just need to know for the exam what isotopes are. What we really want to pay attention to right now is the electron arrangement and what's going on in terms of these orbital shells, because we talked about the neutrons and the protons making isotopes. What's happening with the electrons? Each one of these yellow circles is called an electron orbital. There are many orbitals. We're only showing 2 here. But one of the things to be aware of is in the first orbital, okay, you only have a maximum of 2 electrons that can live in that orbital. In orbital number 2, in the second orbital, you can have 8 electrons. The way I like to think of them is like each one is a neighborhood with houses, okay? This is a real small neighborhood, and there's only enough space for 2 houses in the first neighborhood. In the neighborhood outside of it, kind of more the suburbs, there's more space. There can be 8 houses, okay? There's a third neighborhood even outside of that. Anything above the second neighborhood or orbital can take up to 8 electrons. Every different atom has a different number of electrons, which means each one of these white spaces are vacancies. It's a spot where an electron can go. That also means that if you have a vacancy, this atom can share an electron, so the carbon can share an electron with the nitrogen there, and nitrogen can share its electron with that carbon. So this here would be what we call a covalent bond. The covalent bond is an equal sharing of electrons between 2 atoms. You can see that there's still 3 openings here. Let's say, for example, maybe the hydrogen's going to share here, and that's going to share with the hydrogen. So here you'd have a carbon, nitrogen, and hydrogen. You still have 2 more spots that carbon can interact with 2 other atoms. Those types of bonds are formed through chemical reactions. What's going to happen here is that an atom is going to acquire electrons or share electrons through their outer shells only. One of the things I failed to remember to tell you is that Once this first orbital is full, any new electrons go into the next orbital, okay? If this one's full, though, you're not going to get a reaction. We'll talk about that later. But over here, since you have openings, only the outer orbitals interact with adjacent atoms. These interactions result in atoms staying real close together through chemical bonding. And the example I gave you was through covalent bonding. We're going to talk about ionic bonds first and then go back to our covalents to talk about them in a little more detail. So remember I told you about the chlorine ion being kind of a thief, stealing electrons from other. Chlorine becomes a chloride, it steals the electron. Here's the deal. This is actually, ionic bonds are really fun. Some atoms, like sodium, bump up to the third valence shell, okay? So you have 2, 4, 6, 8, 10, 11. So sodium has 11 electrons, which means how many protons and how many neutrons? For an atom to be balanced, the number of electrons match the number of protons and neutrons. So that means it has 11 protons and 11, oops, let me do this over here. Oh, blast. Oh, this is a new error on my part. Let's see if I can make this happen. Oh, come on. I'm sorry. Okay, there we go. And 11. Oh, it's fighting with me still. I have to get my list up here. Where did my list go? Oh, I'm so sorry, you guys. Okay, I'm going to have to push pause. I'll come back in a minute. Okay, I am still working on this. Let me see if it'll behave now. Yay! I think we're back. Okay. So coming back to our ionic bonds, basically what's happening here in this situation is that chlorine is stealing the proton from sodium. Okay, my apologies, and there we go. I got everything back. Okay, so chlorine, because it has an almost full valence shell, is able to, and it has a more electropositive nucleus. In other words, it has a few extra protons. This little weak electron transfers over to the outer shell, filling the chlorine atom so that the outer shell is completely full, and that becomes chloride. And then sodium becomes a positively charged ion because it lost an electron over here, and now it has one more proton than it has electrons because that electron came over here. What that does is form what we call an electrostatic bond or attraction between the positively charged sodium and the negatively charged chloride. What this also means, which is kind of cool, is that you have ions. When you have an ion is a charged atom. It means that in this case you have an extra negative charge or an electron, and over here you have, compared to the electrons, an extra positive charge. Okay, the positive charged ions or positively charged atoms are called cations. Just remember, cat people are positive people. Negatively charged ions are anions. Cations are positively charged. Okay, because again, these have this attraction, the negative to positive, they just hang together. That's a ionic bond. Covalent bonds are when two atoms are sharing a pair of electrons, and I talked about that before. So one example is with hydrogen. Hydrogen only has that first orbital shell, and within that first orbital shell there are only two vacancies or two places for a house. Each one comes to the party with a single house. They can share the two houses, thus filling that first orbital. That is our covalent bond. We can write it out this way as a line between two hydrogens. That's the structural formula. Ball and stick model or the space filling model, I don't ask you guys to necessarily draw them out. When we talk about things in biology, we do tend to stick with this type of communication. Methane, carbon, and 4 hydrogens. Remember that carbon had 4 vacancies, 1, 2, 3, 4. Hydrogen can fill those beautifully, and that's methane. That's that stinky gas that the cows, not cats, let out. And then oxygen. Oxygen actually can make a double bond between the two second orbitals, and in that way you have you have O2 with a double bond. These double bonds are harder to break than a single bond when it comes to breaking things down through chemical reactions. Hydrogen bonds. Now, this is one that confuses people an awful lot. Hydrogen bonds happen when atoms are attracted to one another, kind of like an ionic bond. But let's say, for example, in the case of water, water is what we call a polar molecule. Okay, the oxygen actually has a valence of 2, so there are 2 vacancies, and of course the 2 hydrogens have a valence of 1, so you have a covalent bond where you have an electron here and electron here being shared. But the problem is that this electron spends more time around the oxygen than around its own nucleus. Okay, so what ends up happening is the oxygen appears to have a negative charge because the electrons from the hydrogens are spending more time over here and fewer time over here, okay? And the hydrogens appear to have a positive charge. Looks kind of like Mickey Mouse's head, with the ears being positive and the head being negative, okay? What's really happening here is the electrons are spending more time around oxygen, and the hydrogens are just kind of hanging out over here. And remember that hydrogen doesn't have a neutron. It's just a proton and an electron. That's one of the things that makes hydrogen super, super talented. We'll talk about that when we talk about metabolism. But the hydrogen, now that this has a positive charge, if you're around another water molecule, the oxygen will align and be attracted to the positive pole of the hydrogen, and then the hydrogen will spend its time around that oxygen. So the way we draw it out are with dots, because it's an attraction, okay? It's not like a covalent bond. And then the same thing happens over here. You'll have an oxygen that has a negative charge, so it's attracted to that hydrogen. Hydrogen here, which has a positive charge, is attracted to that oxygen. And so in this way, what you end up with hydrogen bonds is a structure that's kind of like a net. So when you look at water, hydrogen bonds occur among, oops, that's a G, among, not almost almond, right? Among water molecules. But covalent bonds, and in this case, polar covalent bonds, happen within water molecules. Why is she telling us this? I don't know. That might be the kind of thing that shows up on a quiz, just something to be aware of. Okay, so chemical reactions are the things that make and break bonds. So here's our polar covalent water molecule. Remember, the electrons are spending more time around the oxygen, making it more slightly positive, and protons are hanging out here in space. When you have hydrogen gas, 2 hydrogens together will bond to make H2. Oxygen, remember, has a double bond. These have a single bond. But then when you add energy, these 2 molecules, these reactants, change their organization such that 2 hydrogens will interact with a single oxygen, forming water. And remember, again, positive, positive, negative, positive, positive, negative poles in this molecule. These chemical reactions start with reactants and they end with products. Sometimes the reactions can go back and forth. Don't worry about that right now. Now, one of the cool things about chemical reactions is that they cannot create or destroy matter. They just rearrange it. You're not creating or destroying more hydrogen or oxygen. You're just rearranging the molecules or the atoms to make a new molecule. Actually, you are rearranging molecules, but, so you're just rearranging matter. You are not destroying it or creating new matter. So why do we focus so much time talking about these chemical reactions within our system? Well, these chemical reactions are the reactions that make everything in our body. And these reactions cannot happen without water. Water is essential. Life on Earth started about maybe 3 to 3.5 billion years ago. Modern life cannot exist without water. Your cells are made up of anywhere between 70 and 95% water. If you go below 70%, I mean, even at 70%, you'd be really dehydrated. And so the abundance and the massive amount of water on our planet, even salt water in the ocean, is one of the biggest reasons why Earth is habitable. So that's why astronomers are always looking for planets that have water on them. If there's water, then life as we understand it here on Earth might be able to exist there. So what is water? What are their life-supporting properties? We talked already a little bit about how water is a polar molecule. It's hydrogen and oxygen, and that hydrogen and oxygen within the water molecules, among them, form these hydrogen bonds. That's a pretty cool example, right? And that forms that big net that actually that water walker in that first slide that we were looking at walks on. That's the surface tension. Water walkers balance on the surface tension or the hydrogen bonds among water molecules. Other very important properties of water is the fact that water can dissolve almost everything, all right? We call water the universal solvent. And so lots of compounds, which we also call, so a compound could be something like, I don't know, Jello, okay, which is collagen, actually, a protein. It can also be called a solute because you're dissolving it in water, which is a solvent. The solvent is the thing that does the dissolving. The solute is the thing that is dissolved into the solvent. Water plus a solute is called an aqueous solution. So when you put salt in water, that is an aqueous sodium chloride solution. Now, how do you make things that are bigger? All right. Dehydration synthesis is a process by which you take what we call monomers, okay, mono meaning single, mers meaning repeating units. So you take monomers, you take a hydrogen and a hydroxyl out, put them together, and you end up with water. At the same time, when this occurs, you form a new covalent bond between the two monomers, and now you have what in this case we call a dimer. This dimer, di for two, right? So when you take water out of monomers, you can form long chains called polymers. This is just a dimer because it's two. But polymer, poly for many, mers, stuck together, are formed through dehydration synthesis. This arrow right here usually means that you'll have enzymes plus energy being used. We'll get to that later. Hydrolysis, hydro for water, lysis for cutting, okay? Hydrolysis is where you add water to melt stuff, okay? Here you would be adding water to sugar to make an aqueous solution, glucose solution, okay? And the water, the H2O, like that H and that hydroxyl, will come over here and associate with these sugar molecules. Just so you know, these are sugars, actually. Okay, so these are the kind of the high points of water and how it supports life. Number one, yeah, we have our surface tension, okay, water walkers, universal solvent, and water being able to make and break biological molecules. Another thing that water is able to do really well is what we call buffer. Now, this is one of the cool things about water being H2O. That hydrogen can pop off. One of Mickey Mouse's ears, remember we have the oxygen, which is negative, right? We have the hydrogen, which is positive, and this hydrogen over here, which is positive, Mickey Mouse's ears, right? One of these, I'm going to try to make that look a little bit better there. One of these sometimes can pop off, okay? And you end up with just an H plus and what we call a hydroxyl. What's interesting about this is that the more H pluses you have in a solution, the greater the hydrogen or proton concentration is, the lower the pH of the solution. A low pH means you have an acid, okay? So lots of protons, also called hydrogen ions, hydrogen cations, equals an acidic solution, okay? On the other hand, this hydroxyl has to go somewhere. So hydroxyls, if you have additional hydroxyls, let's say that proton is off doing something. Don't worry about what it's doing right now. If you have additional hydroxyls, you end up with a basic solution, okay? So over here, you have lots of OHs, okay? Giving you a basic solution. So a base is a compound that can take up additional protons, okay, this thing here, and remove those protons from solution. So basically a base has a lot of hydroxyls. It can interact with this proton, this H+, and as that happens, the pH comes back down to neutral. An acid is a compound that can donate protons because it has a lot of extra. So I like this picture here because it has a lot of protons in this glass. The protons can go interact with something, and that'll change the acidity of the compound. So here are lots of hydroxyls, right? And they'll pick up those protons. I tend to call hydrogen cations protons because that's what it is. It's a raw proton out there. So what in our environment is acidic and what's basic? Acidic is pretty easy. We're very used to talking about acids. Lemon juice, gastric juice, our stomach acid can be between a pH of 2 or 1. Let me tell you something. That's enough to etch glass, okay? Your stomach acid is really strong. Urine has a pH of about 6. It's slightly acidic. On the other hand, seawater is slightly alkaline. Household ammonia, household bleach, very, very basic. In fact, it's caustic. Don't kid yourself. Strong bases can melt your skin, okay, giving you a bleach burn. It's a nasty thing. It can burn you as badly as a strong acid. The last thing we're going to just briefly touch on, because I'm going to be talking about organic chemistry in another lecture where we talk about diet and metabolism. Organic chemistry is the field of chemistry where you study carbon compounds, okay, or carbon molecules. Carbon molecules consist of proteins, nucleic acids, lipids, and carbohydrates. Remember, proteins are long chains of amino acids. That's what they're made of. Nucleic acids are long chains of nucleic acid bases, nucleotides, and that's DNA, RNA. It is also actually ATP, GTP, ADP, GDP. So, I mean, there are other smaller nucleic acids other than DNA and RNA. Lipids are made of what we call a head, which is glycerol, 3 carbons and some hydrogen, and then long hydrocarbon chain tails, okay? We'll look at that in a few minutes. And then carbohydrates are long or short chains of sugar, glucose or fructose, okay? What do these things do? Small molecules, you don't need to worry about that right now. Vitamins, neurotransmitters, things like that. What's the function of a protein? Structural. Mostly structural. Your hair is pure protein. Your skin, tons of protein. When you think of the word protein, I don't want you thinking of chicken or carne asada. I want you thinking of chains of amino acids. We're going to think like chemists here. In addition to being structural, proteins can be enzymes, and we'll get to that again later. Nucleic acids store information. Nucleic acids can also act as an enzyme or in energy transfer in terms of ATP, okay? Lipids, they store energy. They do provide insulation cushioning, but lipids can be converted to membranes. So one of the things that we talk about a lot dietarily in terms of a healthy diet is the good fats and the bad fats, all right? The good fats actually can help maintain your membrane integrity, your cell membrane integrity. Bad fats do nothing but clog up your arteries. It's a bad deal. Carbohydrates are almost entirely energy sources. You can store energy with your sugars. We, in humans, our sugar, our big energy storage molecule is glycogen. Glycogen is the human form of starch. Plants make starch. We make glycogen. It looks a heck of a lot the same biologically and chemically speaking. And carbohydrates form structure, and they don't have, I don't have it in this slide, carbohydrates can also act as a recognition marker. I have my own personal val carbohydrate on the surface of all my cells, a protein carbohydrate, so that when my immune system is floating around out there and my white blood cells are checking out all my cells, they say, oh yeah, this is Val's, it has her tag on it. So everything, in your body has your own personal Gucci tag that you've made, and your immune system looks for your Gucci tag, says, yep, that's my Gucci, and moves on. It's when it finds, like fake Gucci in your system, like, I don't know, E. coli from another organism or staph, right? That's fake Gucci. Your immune system goes, oh, fake Gucci, we got to get rid of this. We don't carry fake Gucci around. So another picture, and the last picture that we'll be looking at, are the macromolecules, carbohydrate, sugar. This is a basic glucose molecule, which has 6 carbons on it. Each one of these points is a carbon. Stores energy, structural material, and an example of a large carbohydrate polymer would be starch in a potato. Carbohydrates taste really good, right? Especially when you pair them with lipids. Lipids consist of this group right here, which we call a glycerol. And these are the fatty acid chains. Fatty acid chains can come in a what we call saturated or unsaturated format. Here, these little kinks are showing you unsaturated. When it's straight, it's saturated. We'll talk about that later when we talk about membrane structure. What do fats do? Store energy. They do form the membrane, gotta have that. And they make steroids. Steroids, you might think only of estrogen and testosterone, but there are a lot of steroids like human growth hormone that help us grow. Fat, lipids get stored in fat cells, essential for insulation in this organism, a sea lion. These guys spend a lot of time in the ocean. It's cold there. The fat helps keep their body warm. Proteins, this is like, I know this looks kind of like a mess, but remember, proteins are chains of amino acids. They can be structural, like hair in this little girl. Peptides are small proteins, so peptides are less than or equal to, actually I'm drawing this in the wrong spot. Let's do it this way. Peptides are less than or equal to 99 amino acids. So if you have 99 or less amino acids in a chain, that's a peptide. A protein is greater than or equal to 100 amino acids in length. So basically, a peptide's a really small protein. And then the last one, nucleic acid, stores genetic information, also deals with energy metabolism in terms of ATP. And it's a nucleotide associated with some other goodies, all right? So we will start on the next chapter soon. In this particular chapter, spend some time just looking up what are the macromolecules, what are the monomers of those macromolecules. I want you to understand dehydration synthesis and hydrolysis. Understand the different types of atomic bonds, your ionic bonds, your covalent bonds, polar covalent versus just your regular covalent, and the subatomic components. This will all show up in your quiz at the end of the week, and I hope you have a great day.